Hello everyone, my name is Finding Pepper and welcome to episode 2 of my 3D rendering Scratch tutorial, in which we will be drawing a filled triangle. Now this process is a lot harder than it sounds, and it involves quite a bit of geometry, especially if we want our triangle drawer to run at any sort of reasonable speed. But it's really important that we take the time to do this, because it's what will allow us to draw solid 3D objects. Thanks to Chromecat, Rex, and Geotail for their trifill algorithm. Let's create a little demo project for our trifill, so we can easily see it in action. Make a block called trifill. We'll need inputs for the XY position of each of the 3 vertices. Add inputs AX, AY, BX, BY, CX, and CY. Make sure to check Run Without Screen Refresh, so this block runs as fast as possible. We'll start by drawing an outline of the triangle. To do this, we'll need to add the pen extension. Start with pen up and set pen size to 2. Go to the first vertex, so that's AX, AY, pen down, and then go to BX, BY, then CX, CY, and finally back around to AX, AY, pen up. Then, when flag clicked, use this block. Put in whatever inputs you want. I'll do -100, -100, 0, 50, and 200, 0. Run the project, and there's our triangle. Great, we drew a triangle. Hope you enjoyed this tutorial. Have a great rest of your day, and goodbye. Okay, no, we've got a lot more to do. We actually have to fill in the triangle. But before we do that, let's add a way to easily change the shape of the triangle, so we can check our drawing code is working well. Triangles are defined by 3 vertices, so let's make a list to hold the X and Y positions of each of these vertices. I'll call it vertices for all sprites. Manually add 6 zeros to the list, so all 3 vertices will be at 0, 0. Each pair of values represents an XY coordinate. Now create a new sprite to be little circles on the triangle's vertices that we can drag around to change the triangle's shape. I'll change the costume to be a small circle with a number 1 in it, like so. Then duplicate this twice, changing the number inside to a 2 and a 3, respectively. Make sure these costumes are numbered 1 through 3, so we can switch costume easily. We'll use clones to make 2 of the vertices, and then the main sprite will be the 3rd vertex. So when flag clicked, switch costume to the first costume, which I haven't renamed, so it's just costume 1 for me. And then we'll make a variable called vertexNum to hold which vertex each clone represents. Now, we'll repeat twice for our 2 clones, and now we want to go to the position that the vertex should be at on the triangle, and that position is stored in the vertices list. So go to Item, and then we'll want to use our vertexNum variable, and then multiply it by 2, because remember there's 2 pieces of data for each vertex, an X and a Y. Then add 1 for the X, and then duplicate this for the Y and add 2 for the Y. Now create clone of myself. Then we'll do next costume and change vertex num by 1 to get ready for the next vertex. Then after that loop, we want to make sure the main sprite, that is the 3rd vertex, is positioned correctly as well, so just duplicate this goTo block and put it at the end of the repeat loop. Now we want to be able to drag these vertices around, so when this sprite is clicked, we'll repeat until our mouse is no longer down, and just go to mouse X, mouse Y. So that's all the dragging done, but then we also want to update the corresponding vertex in the vertices list, so our triangle displays correctly. So replace item, and then we can take our formulas involving vertex num from the goTo block. So replace item, vertex num times 2 plus 1 of vertices with mouse X, then duplicate this change the +1 to a +2, and the mouse X to a mouse Y. Now we also only draw our triangle at the very beginning, but we want to redraw our triangle after we move one of the vertices around. So here, let's broadcast a message called redraw. In the triangles fill sprite, when I receive redraw, we'll erase all and then use our trifill block. The inputs to this block will be the items in our vertices list. So item 1 of vertices for the first input, then item 2 of vertices, item 3, item 4, item 5, and item 6. And we'll also broadcast redraw when the flag is clicked, rather than using our trifill block. Run this, and there you go. Now we can drag around our triangle. Okay, this looks really nice. And with that done, that means it's now time for the fun part, actually filling the triangle. One obvious option for how to do so is using what is known as a raster fill, where a series of parallel lines are drawn with no space between them until the triangle is filled. But drawing all those lines takes time. Our goal is to fill the most area in the least time, and to do this, we'll need to get very clever with our drawing. The Scratch pen can draw two things: lines with rounded edges and circles. It makes sense then that the first thing we want to do is to draw the biggest circle we can. That way we can fill a whole bunch of area with just a single pen down. The biggest circle that can fit inside the triangle is shown here, and it's known as the incircle of the triangle. To draw it, just like with any other circle, we need two pieces of information: its center, fittingly called the incenter, and its radius, which is called, you guessed it, the inradius. Let's start by figuring out how to find the incenter. And to do this, I'll start by looking at a very simple case, an equilateral triangle. Here, the incenter is the same distance from each of the points, and in fact it's the average of the 3 points. When we move 1 point farther away though, you'll notice the incenter doesn't move very far. It's clear that here the incenter is no longer just a simple average of the 3 points. The point farthest away has less effect on the incenter's position. That might indicate to us that instead of a simple average, we want a weighted average. That is, some values we're averaging have a greater effect on the final average. To write a weighted average mathematically, we multiply each term we're averaging by a certain weight, then add them together, and then divide by the sum of the weights. But what should these weights be? Well, moving the vertices around a little more, we might notice that the effect a point has on the incenter's position has to do with how long the opposite side is. If the opposite side is really short, like here, the incircle tends to be pretty far from that point. If the opposite side is really long, like this, it tends to be quite close to that point. So let's use the lengths of the opposite sides as the weights in our average, like so. We divide by the sum of the weights, which is just the triangle's perimeter. Thus, we get our incenter formula. Now to find the formula for the inradius. I'll call the incenter point I and each of the vertices A, B, and C. If we draw lines from the triangle's vertices to the incenter, we get 3 smaller triangles. Because the incircle is tangent to each of the sides, meaning it touches each side at exactly 1 point, we know that a line from the incenter to where the circle touches a side will be perpendicular to that side. So the height of each of our 3 triangles is this inradius. Each triangle's area, which I'll denote using square brackets, is then the length of the side it's built off of, which we know, times the inradius divided by 2. That's just using the standard triangle area formula which we all know and love. Now if we sum the area of the 3 small triangles then, which we know is equal to the area of the large triangle, we get the sum of the side lengths times the inradius. We can rewrite this as the radius times the semiperimeter, which is, as the name suggests, half the perimeter. Now we just need to find the area of the large triangle. To do this, we can use the infamous Heron's formula. If you've taken geometry in school, you've probably learned this formula and then promptly forgot it. So to refresh, Heron's formula is shown here, and it gives the triangle's area in terms of its side lengths. It also makes use of the semi-perimeter, denoted S. Plugging this into our earlier equation, we get that the in radius equals the square root of s minus a times s minus b times s minus c over s. Let's put our formulas into Scratch. Create variables to hold the three side lengths. All the variables we make here will be for this sprite only. So make side AB, side AC, and side BC. Finally, let's make a variable for our semi-perimeter, called semi-perimeter, so we don't have to recalculate it each time we use it. Alright, to find the length of a side, we can use the distance formula, which comes from the Pythagorean theorem, and again, if you've taken something like algebra, you probably know this distance formula. So set side AB to the square root of, then get a plus and a times, ax minus bx squared, so we can just duplicate that, so ax minus bx times ax minus bx, and then add to that ay minus by times ay minus by. And that whole thing is inside the square root. Now we can duplicate this for side AC, changing all the references to b to c. So ax minus cx squared plus ay minus cy squared. Then finally duplicate it for side BC, where we have bx minus cx squared plus by minus cy squared. Alright, now set the semi-perimeter to the sum of the side lengths, that's side AB plus side AC plus side BC, all divided by 2. Alright, now we can make a variable to hold the in radius, and I'll just call it radius because we'll be scaling that for the outer loops. So set radius based on our formula that we discussed, the square root of, then we have semi-perimeter minus side AB times semi-perimeter minus side AC times semi-perimeter minus side BC. And then we divide all of this by semi-perimeter, and we put it in the square root. Alright, now for the in-center, we don't need variables for this, we can just use the built-in x and y variables to go straight there. Set x, and then we'll want to take our weighted average that we discussed, that's side BC times AX, plus side AC times BX, plus side AB times CX. All divided by the perimeter. And rather than calculating the perimeter again, let's just use the semi-perimeter times 2. Now duplicate this for set y, and just change all the x's to y's. So ay, by, and cy. Now set pen size to radius times 2, because pen size is in diameter, not radius. And then pen down. Try this out, and there we go. There is the Incircle. It's looking quite fine. We can move our vertices around, and you can see the Incircle moves around with them. This is all looking really good. Alright, now we need to fill in around the Incircle. To do this, we'll loop around the triangle's edge, drawing smaller and smaller lines until the corners are almost completely filled in. The corners will never be 100% filled, but we can get close. So that our lines can fit as far into the corners as possible, we want them as small as possible without leaving any holes. What this smallest thickness is dependent on the distance from the farthest vertex to the incenter. That's because there's more area to fill in the corner towards the farthest vertex. To find our desired pen size, let's look back at our triangle. The desired pen size will be this distance PQ. This is the smallest the pen can be without leaving any holes right next to the incircle. To find that distance, PQ, we can look at these two similar triangles. If triangles are similar, the ratio of corresponding side lengths will be equal. So PQ over R, where R is the in radius, equals AP over AI, where I is the incenter. Because AP is just AI minus R, PQ equals R times AI minus R over AI. Now AP is the diameter, but what we really want is the radius, which I'll call X. The radius is just going to be half the diameter, and you can see how we want the new smaller pen to fill this corner nicely. In fact, if we zoom into that corner, we see it looks very similar to our larger triangle. This means we can just use the same formula but with our new radius to get the radius for the next iteration around the circle's edge. You may notice that we use the radius twice, but one of these uses is in a ratio that stays the same no matter the depth. So we can define a scaling factor as AI minus R over 2AI and repeatedly scale the radius by this factor. But the radius isn't the only thing we need to find. We also need the coordinate of where the smaller circle fits into the corner. We can treat this coordinate as an offset from where the vertex is. That is, something to add to the vertex coordinate to get the desired position. Furthermore, we want an offset that we can scale by the radius. Because each smaller circle is essentially a scaled down incircle, we can just take the offset from each vertex to the initial incenter, which we get by subtracting the vertex coordinate from the incenter coordinate, and then divide that offset by the in radius to get a sort of base offset. We can multiply that base offset by the radius at each level to get each offset, which we then add to the vertex position to get our desired positions. Alright, so hopefully that wasn't too complicated. I invite you to maybe rewatch that again if you didn't fully understand it. Or, alternatively, ask a question in the comments, which I know nobody does, but I would be more than happy to answer them if you did. But anyway, let's put that into code. Start by adding an input to the tri-fill block called resolution, which will influence how many times we loop around the triangle's edge. Where we use this block in redraw, put a 2 in the resolution input. Up at the top in our initial outline, let's set the pen size to resolution instead of 2. So if our resolution is bigger and therefore worse, the outline will be thicker to compensate for it. Now to find that radius factor we talked about. So let's make a variable to hold that, called radius factor. To find it, we need the distance to the farthest vertex from the incenter. And the farthest vertex from the incenter is the one opposite the shortest side. So let's check which side is the shortest. I'll start by checking with an if-else and an or if side AB is less than side BC or side AC is less than side BC. So essentially, if BC isn't the smallest side. Now if BC isn't the smallest side, then either AB or AC is. So let's just check that. If side AB is less than side AC, that means that side AB is the shortest. Now we can calculate our distance, and rather than making a separate variable for this, I'll just store this temporarily in the radius factor variable. So set radius factor to, and then we'll use our distance formula again. Now if you remember, the incenter isn't stored in a variable, it's stored in the sprite's x and y position. So our distance will be, using the distance formula, the square root of x position minus cx times x position minus cx, so that's just squaring it, plus y position minus cy times y position minus cy. Okay, so that's the distance from the incenter to vertex C, because vertex C is the one opposite the shortest side, side AB in this case. Now, in the case where side AC is the shortest, that's in this inner else, we'll want the distance to vertex B. So just change all the C's to B's. Now, in the outer else, side BC is the shortest, so we want the distance to vertex A. So just duplicate the set radius factor and change all the B's to A's. Okay, so that's just the distance from the incenter to the farthest vertex. That isn't actually the radius factor we want to find. So let's set radius factor to, and then we'll set it in terms of this longest distance. That is radius factor minus radius divided by 2 times radius factor. So that's the formula we talked about, and then we multiply the radius by that to get the next smaller radius for the next loop around the triangle's edge. Okay, now to find the incenter's offset from the vertices, to find where the lines around the edge should be positioned. We'll make variables for each of these offsets, for this spread only, called offset AX, offset AY, offset BX, offset BY, offset CX, and offset CY. Now we need to set all of these, so set offset AX to, and then X position minus AX, that is the incenter's position relative to vertex A, and then divide that by radius to get the base offset. Then duplicate this for offset AY with y position minus AY over radius. Then for BX, that's X position minus BX. For BY, that's Y position minus BY. For CX, that's X position minus CX. And for CY, that's Y position minus CY. Okay, that's all our offsets set. Finally, we can do our loop around the edge of the triangle. So we'll repeat until the radius is less than resolution. So that means the smaller resolution is, the more times we'll loop, and the higher quality our triangle will be. Now the first thing we're going to do each loop is scale down the radius. So set radius to radius times radius factor. Now set the pen size based on the radius. Set it to radius times 2, because we want the diameter for the pen size. And then add 0.5 to that, just to make sure there's no tiny holes or anything popping up anywhere. Then we'll go towards vertex A. And remember, to find the coordinate that we want to be at, we multiply offset AX by the radius. So go to AX, and then we're going to add to the position of vertex A our radius times the offset AX. Then duplicate this for Y with AY plus radius times offset AY. Then duplicate this and change all the A's to B's. Then duplicate it once more, changing all the B's to C's. Then finally duplicate our initial one for vertex A to just go back around the triangle back to our vertex A. So we make a full loop around the triangle. And then the repeat until loop will go down to the next smallest radius, and then loop around the triangle again, and then keep repeating that until it gets to a small enough radius, and then it'll stop. And we'll have a quite nicely filled in triangle. Alright, so that is all our tri-fill code done. Let's set the pen transparency to 50, so we can see how each layer overlaps. Run the project, and now we have a fully filled triangle. If we set the pen transparency back to 0, then it looks nice and solid. Now, this might have seemed like a lot of work to get to a relatively underwhelming result, but I assure you, this fast triangle fill algorithm will be necessary to having a good, and not painfully slow, 3D renderer. In the next episode, we'll use the triangle filler to render solid 3D objects. We'll also cover backface culling, Painter's algorithm, and triangle clipping, so keep your eyes out for when that video releases, probably in a couple weeks. Thank you so much for watching, have a great rest of your day, and goodbye!